Okay, salam alaikum, shabab. Welcome back to the classroom. And let's start talking about the second example about superposition. Hopefully, you understood from the other example, which was very simple, how we deal with superposition. This one is a little bit of toward the heavy side of the superposition problem. So please watch out and be careful here. This problem says that use the superposition to determine the expression for the slope at point A. This is point A, right there, the free end, and the deflection at point C. So basically, what are we going to do? In this problem, we have been asked to use superposition. Some other problems, in life, you may not be asked. You can use different ways, but in here, you were actually requested to use superposition. So as you see, there is a concentrated load, which is a function of W, which is called W0L. And here we have a pin end, here we have a simple support, and here we have a distributed load of W. That distributed load is going from A to B. And what we see here that this beam is segmented into 3 segments, each one with an equal length of L, okay? So what I want you to understand is that if you were to imagine how this beam will deform, somebody would expect that this is gonna go like this, and then it will drop down and then go up like that. So as you see, this is the end delta that we want to calculate. And in here, we want to find the slope, which is the, how much angle is this going to be rotating with respect to, okay? So this is basically what I just showed you. This is how we think the beam will deform. As I said earlier, you may not see this in real life with your own eyes, but this deformation actually happened. So what I want you to understand is that this problem is going to be divided into 3 problems. Let me explain to you why. Let me go back. The first problem is this. If we go to the solution in the back of the book, we will see that there is a solution provided for a beam which is with a free end and cantilevered end, and with a uniform distributed load. That actually exists, okay? Now, we know that this beam will bend like this. Is that right? Now, what we need to imagine is that if I want to clear this out for you so you don't get confused, we are going, now, usually as we do, when we cut the beam here, we substitute the beam end with what? With a reaction shear and a reaction moment. Those reactions are exactly the same reaction in the solution for a cantilevered beam in the back of the book. Okay, in the back of the book, a fixed end, which is cantilevered, that end will have a reaction at the end, reaction force and a reaction moment. So this means we can use that solution, although in here there is no end, but by cutting the beam. Now, and the distributed load will act downward, and the beam will deform in this manner, okay? That's basically what we are doing. Now, if we use the book solution, what are we gonna get in there? At point A, we want to find the slope. So we don't need Y maximum. Y maximum is the amount of distance this is gonna go down. That's why, delta maximum or Y maximum. What we want is the slope. So in order to get the slope, what are we going to do? We are going to use the equation, which is y equal to something, something, something. And then we will take the derivative of this equation with respect to x, because actually in here we will have x squared x, and then we substitute this in a proper length. Do you understand that? And this is basically theta, the change of dy over dx. That's the slope. So that's what we are going to do at this end. Now, but if we only cut this beam, okay, then somebody would ask and say, how would this beam be affected? How would this end be affected if I look at the other segment of the beam? So the other segment, I have to solve it as well. Now, for the other segment, how are we going to treat it? Like this. Now, that's a very tricky part, you know? So look, forget about the concentrated load. I am now looking, this one is L, this one is L, and this one is L, so it is 2L. I'm now looking from B to D. Now, if I take the reactions in here, then I would say that this is a reaction like this, and this is a reaction like that. Is that correct? So if that's the case, then I can treat this problem, this part of the problem, as, you know, now look carefully over here. If you have a beam like this, and then right here you apply a moment like this, the beam will deform, and that deformation will affect that end, will affect this, everything. Do you understand? So what are we going to do? We are going to treat this problem, okay, as a beam. So we are going to solve it this way. We are going to solve it number 2 this way. And number 3, we are going to solve it as a beam like this with a concentrated load. Now, look at me. Watch out with me over here. Now, for this beam, if you consider the remaining part under, you know, fixed load, then what will happen? You know that the beam will deform like this, but when it reaches to this point over here, the slope will become straight. Do you understand that? Because after this, there is no force here applied, because now I am using superposition. I am assuming only this force is being applied. And for that, there is going to be slope, there is going to be deflection. But after this, there is going to be a straight line, which means if I determine the slope in here, this slope is just going to continue straight. So that's why when I solve the third segment, I will only focus on this part of the beam only. I don't need to worry about the other one. Why? Because once I determine the slope here, it's just going to be the same everywhere. You understand that? So let me go to the solution. Now, if I go to the solution, okay, the first solution will be like this, all right? So I have in the back of the book, I have a solution for a cantilevered beam, I mean, and a distributed load, which is W, over a length which is equal to L, okay? Now, what are we interested in is we are here thinking that this is point B and this is point A. Just to remind you, okay, that's point B and that's point A. Okay, now we know that the deflection of the beam will be like this. And basically, we are going to call this angle that we will determine as theta A small a. All right, how do we find this angle? As I told you, what are we going to do? From the back of the book, the solution says that y is equal to wx squared divided by 24ei, and then 4lx minus x squared minus 6l squared. Now, so how am I gonna solve this problem? First of all, you should remember here that L in the equation is the same as L in the problem, because this segment in the problem has a length capital L. Okay, now, so what I'm gonna do, I will say that theta A is equal to the change dy over dx, okay, which is equal to d over dx of what? Of this equation. Now, this equation is wx squared divided by 24ei multiplied by 4lx minus x squared minus 6l squared. Now, at what? I will substitute here that what? X equals to L. Now, you may ask a question. Should X be L or should X be 0? Now, be careful. In the back of the book, the solution says that the fixed end is the origin, with this one being Y and this one being X. So the free end has a length of L. The fixed end based on X has a length of 0. Now, if you go back to our problem, this is the fixed end. Then what is the length of the free end? Is L, capital L. And that's what we are going to do. That's why we are putting X equals to capital L. Now, without, doing this by hand here and wasting the time, you can do this at home. The solution will be W 0 and L cubed divided by 6EI. That's theta AA. Just remember this. Okay. Now, let's go to the next part. Now, the next part is going to be a very simple one. Now, let me tell you, what is it? If you go back to the book, again, back of the book, you will see a solution for Y and X such that there is a reaction R1, and here there is a reaction R2, and the beam is simply, subjected to a force F at a distance which is L over 2 and L over 2. So the total length is L. Good? All right. So what are we going to do here? In this one, we are interested in knowing how much is this. So we are going to call this delta C, which is buoyant C. Why buoyant C? Look, this one is buoyant C. And we will call this step number B. Our letter B. We call the first one is A, this is B. And not only this, as I argued earlier, that the slope here will continue the same in a straight line. So we are going to call this theta at point B, but from step B, small b. Good? Okay. Now, the thing that you need to remember very well is that this L over 2 and this L over 2 are coming from the solution in the back. But in the problem, we have capital L here and capital L here. So you need to be very careful. Okay. Now, also, in our solution, F is equal to W0 capital L. So that's what we are going to do. In here, we are going to substitute this. And the length L is equal to twice as capital L, 2 L's, okay? Now, the solution is as follows. Theta B capital B is equal to, how am I going to do this? I'm going to take the derivative d over dx of the y equation. In the solution, I have y of a b. where this is A and this is B. So what I'm going to do, I will go and find that equation. That equation is basically fx divided by 48ei, okay, multiplied by 4x squared minus 3l squared. Now, when I take the derivative of this, I just need to make sure that I substitute f as w0 capital L, and the small l equals to 2 capital L. If I take the derivative and then substitute, I will find that this angle theta capital B is equal to W0 L cubed divided by 4EI. I hope this is now clear. Okay, now what is the last thing? Is what is this? This one is very simple. Why? Because the Y maximum equation, this delta CB, is equal to the Y maximum equation, which is equal to minus FL cubed divided by 48 EI. Now, again, I have to substitute F as W0 capital L, and I have to substitute small l as 2L. And if I do that, I will get minus W0 L to the power 4 divided by 6EI. Good? So we're done. Now let's move on to the last segment, okay? Okay, the third part, I'm sorry. The third part, ya akhwan, I want you to be, very careful here with me, okay? Now, what did we do so far? We took the entire beam, okay? And then we splitted it into the following problems. So the beam originally had a distributed load and a concentrated force. So what did we do? We said solution number 1 is a concentrated load, and the other solution is a little, look, this is A, B, C, and this is D. So for concentrated load, we focused from B to D, and this is point C. For the distributed load, we solved it as A and B, right? As if this distributed load is only applied on that little segment. But the reality, there is a third one, which is this. Let me show it to you. This part is B, D, and of course there is point C in the middle. But the problem here, while this is a fixed end condition, and here this is a roller, and then this is free, the other one here, the other point is free. Here we have a fixed and roller. Here we have a fixed and roller. But what are we going to do? If we take only that part, then how are we going to substitute the moment? Do you understand that? So it's like you are splitting this, as I explained in the beginning. You're taking it into two halves, one half over here, or one part with the applied moment. The other part, when you put it alone, nothing will happen. But in reality, you want to know what happened to the other part, okay, due to the effect of this one. So how do you do that? Well, very simple. What do? You substitute the distributed load in here by a moment. Do you understand? There is no point to put a force at point B, because the roller will oppose it. There is no translation here. but the effect of that distributed load being represented as a moment at the end is going to affect the remaining part of the beam. So what will happen? If we consider this, then the beam, somebody will expect that if the beam is fixed from this side and free from this side to rotate, then the beam due to the moment will rotate like this. Now look what happened. Point C will jump up. That is going to be called delta C for step number C. Now, again, look, the slope here will go like that. So this is going to be, sorry, let me clean this up. This part is going to be, okay, theta at point B from step C. Do you see that? Okay, now the question, what is the solution that we are going to use to solve this problem? Now, this solution, I don't think it exists in your textbook. And don't be surprised, that's possible. Even in some exams, you might get the those little solution combined, listed together for you, and then you try to take them and solve the problem in hand with them. So what is the solution? Let me show it to you. The solution that we are supposed to have is y. Again, this is x. Then we have a beam which is sitting on a roller and a fixed end. Its length is a small l. Let me make it with a light color over here. It's being subjected to a moment m. And what are a combining solution? Y is equal to mx divided by 6e il multiplied by 2l square minus 3lx plus x square. And y maximum is equal to ml square divided by 9 square root of 3 multiplied by EI. Okay, now, so what are we going to do? First of all, you should know that M, which is this, is equal to what? Is equal to the distributed load W multiplied by the length multiplied, because look what happened. In here, the distributed load is like this. So let me show you the problem. So this is the distributed load. The intensity of the distributed load is W0. And this distance from here to there is L. So if we represent this by a concentrated force, this concentrated force has a value of W0 multiplied by L. And this distance is equal to capital L over 2. Now, if I multiply this force by this distance, I will get the moment applied over here. And that's what basically I'm going to do. So this is W0L multiplied by L capital over 2, okay? Which is going to be equal to W0L square over 2. What is the length of the beam again? L is supposed to be equal to 2L. Good. So from this, I will get theta at BC is equal to d over dx multiplied by mx divided by 6EIL multiplied by 2L squared minus 3LX plus x squared. Now, if I substitute, be careful over here. This is x, and I want to find the slope at this point. Now, here, this point x is equals to 0. You see that? So in here, I need to substitute x as it is equal to 0. And then L is equal to 2L. And of course, you will substitute this moment in here. Do you see that? So if you do the substitution, you first take the derivative and then do the substitution, you will end up with W0 L cubed divided by 3EI. Good. Now, what is the delta, right? Now, this moment, as I said, is going to cause this to curve like this. So this is the delta. Now, for the delta, I hope I still have space. Now, delta CC is equal to the Y, which is the Y maximum, okay? Or what you can do, you can take the Y equation and substitute it at X equals to L, okay? If you do that, you will get this as W0 multiplied by L to the power 4 divided by 8EI, okay? Now, the final answer is this. For the slope, the distributed load, okay, is going to make it curve down. The concentrated force is going to make it curve up, right? And the applied moment, which is like this, is going to make it curve down as well. So what are we gonna have? We're gonna have to make sure that we actually make sure that we add everything together, or as I'm gonna show you next. So yeah, so what I was saying, so theta A, from this it's going to go down, from this it's going to go down, from this is going to go up. So if we call theta downward as positive, then we will end up with theta A as positive, as you know, down, minus, which is up, theta B, and then plus, which is down again, theta BC. And if you find this, you will get the answer as W0 L cubed divided by 4EI. As for the displacement, delta C, we got two displacement. One of them is downward and the other one was upward, correct? So what is the solution over here? It is going to be the one which was downward is from the step B, which is minus delta C at small b, and the one which was upward due to the curvature, this is the one which was upward, it was delta C, and if you subtract these, you will end up with minus W0 L to the power 4 divided by 24 EI. Okay, that's it. Now, the next part that we would like to introduce to you is the strain energy density, which is going to be the gateway to solve problems using Castigliano theory. Now, the strain energy density, Juan, is as simple as this. If you recall from the stress strain curve, okay, we call the energy under the curve, or the area under the curve, it's actually an energy. Now, since we are talking about elastic deformation, we will constrain ourselves to this energy in red, which is actually called the strain energy, or sometimes it is called the strain energy density. Now, the strain energy is related to the area under the stress strain curve. Now, when we talk about deformation, here we're talking about displacement. So we can express this in terms of displacement. And to make it simple for you, in here, what do we have? We have this, the energy is going to be called U. Capital U is the strain energy. Now, the strain energy for tension, compression, and torsion, طبعا يا شباب, tension and compression is the same. The energy will be stored in there. And remember, there is no negative energy. There's no negative energy. If you do compression, okay, the stress strain curve will go like that. And in the elastic region, you can still integrate this and get an area. So the notion of negative energy doesn't exist. For that, for a uniaxial tension or compression, the energy is expressed as F squared multiplied by L divided by 2AE. Okay? Or, look, if we want to take this as step by step, why? For example, let's assume that we have a beam which is, you know, as the length changes, okay, the area changes with it, for example. So in here, we cannot assume that L is constant and A is constant. Sometimes we cannot assume even that E is constant. So what are we going to do? In order to integrate over a linear, you know, line, we are just going to focus expressing as an integral, which is what? It is this, or look, U is equal to the integration of F squared, and then what did we do? We put dx. The L is gone. Why? Because if we define the integral from 0 to L, then F here is constant with respect to dx, if it is constant with respect to x. 2AE are constant with respect to x. So what will happen? You will get x. If you integrate, I mean dx, if you integrate, you will get F squared divided by 2AE multiplied by x from 0 to L. And if you substitute L, you will get this equation back. Do you understand that? So this is the strain energy for torsion. It is T squared L divided by 2GJ. And you can also, again, do it as an integral form. Now, I am going to go fast on this. Why? Because we decided in this course to focus on the using Castigliano theory to solve problem for deflection due to bending. Usually in the past, we used to give examples and question about problems when we have tension, torsion, compression, bending moment all together. And then we ask a student to find the deflection. Now we said, okay, let's only use it for bending. So this is the strain energy for a shear. This is a pure shear element, which is subjected to a shear loading. And this is the most important one, which is the one for bending. So the bending, U, the strain energy due to bending, equals to M squared multiplied by L divided by 2EI. I'm sorry, my slide might confuse you. This is I and L. And then which can be written as U equals to the integral of M squared dx divided by 2EI. Okay, remember the strain energy. This is the one with direct shear, if you have a direct V. But as I said, this is not very important now. What do we want to do is this. Castigliano, he's an Italian engineer and scientist, made a hypothesis, okay? Or a theory, if you want to say, which says that, I mean, I'm going to read it very carefully and I hope you can focus with me. What does Castigliano theory says? It says that, okay, when forces act on elastic system, so that's a key word, elastic system, subjected to small displacement. Now, this is funny. You may tell me, how comes? Why does he need to say small? Is there an elastic and not a small? Oh, yes. A fishing rod, ya shabab. Fishing rod can deform very significantly, yet it is elastic. It stays elastic. So we're not talking about fishing rod. Okay, صيادة السمك يا شباب. No, we are talking about a small displacement problem and elastic regime. Look, it says the displacement corresponding to any force. That's the key point. Because the whole fuzz about displacement is to find this little delta or slope. So what Castigliano says here, that we can find this displacement in the direction of a force. And this is very important restriction. What Castigliano is saying is that if there is a body being subjected to a force, then the displacement in the direction of the force, that force, you may ask me, how about the displacement in any other direction? No. In the direction of a force is equal to the partial derivative of the total strain energy with respect to that force. Do you understand? Let me give you an example, very quick one. Let's assume we have a beam, okay? And this beam is being subjected to compression, okay? And transfer load, which is causing it to bend. And maybe here a bending moment, and so on. What Castigliano is saying to you, okay, now we know that this force is gonna cause what? Deformation, which means elastic energy. Let me call it F. So this is the elastic energy due to F. And this one is a moment. So this moment will create an elastic energy due to moment. This one is another force, F2. So what are we gonna do? We're gonna have a strain energy due to F2. Let's assume there is a torsion. Torsion will cause a strain energy due to torsion. So what Castigliano is saying, he's saying, go and sum all of the strain energy. This one, this one, this one, and this one. All of them. Sum them up. And then tell me, where do you want to find the displacement? Let's say, for the sake of simplicity, we want to find the displacement in here. Now, we know that the displacement at this point is going to be affected by the torsion, the bending moment, this one, all of them combined. So what are we going to do? We're going to say that U total, and then we'll take the derivative of that with respect to F. Do you see this? And what are we going to get? We're going to get the displacement in the direction of F. If I want to find the displacement at the place where the moment is applied, do you know what will happen? I can take the derivative of the total strain energy with respect to the moment. In that case, moment cause what? Cause rotation, slope. So I'm going to find the slope that correspond to that moment. Not that correspond to that moment, that is in the place of that moment. Now, somebody might ask me a question. How about if I want to find the displacement in here? There is no force, no F, no torque, no moment. So what should I do? Well, that's the nice trick. I'm gonna ask you, what do you want to find in the green location? What do you want to find? Do you want to find delta? Or do you want to find the slope? If you tell me, I want to find how is this gonna go down, which is delta. So what I'm gonna tell you, go and put a fictitious force F, or as the book call it, Q. What's the story? I'm gonna tell you. We're gonna sum the strain energies from everything, but we will take the derivative with respect to this fictitious force. And you may tell me, fictitious mean imaginary. So what I'm gonna substitute that? We're gonna substitute it as 0. Later, after before solving the problem, we're just gonna plug it as 0. Now, if you want to find the slope in here, then you should substitute a fictitious moment. Why? Forces give you what? Give you deflection, millimeter. Moment give you slope in radian. Do you understand that? If you want to find how the angle is twisted, you should put a torque. Now, to make it simple for you, ya shabab, what are we interested in bending? So we're not going to talk about torsion. We're mostly going to talk about moment and forces that causes bending. Do you understand? Okay. Now, so let's move on. So this is basically what the theory is saying. It's saying that the displacement delta I in the direction of Fi is the derivative, the partial derivative of the total strain energy density or total strain energy with respect to that direction of the, that direction of the force. If you want rotational displacement, then theta I is equal to this total strain, the derivative of the partial derivative of the total strain energy density with respect to moment mi. Now, I know this may not sound very, simple to you. So let me show you an example right here. If we want, look, this is the most important equation. The other ones are for forces. Here, as I told you, we are going to use this only for bending. If you look at the syllabus, it says only bending. So what are we going to do? We are going to focus on, I didn't actually wrote down the moment, but let me tell you this. If you have a bending moment, a beam, which is under bending loading, and let's say you want to find the deflection, delta, the linear deflection, in millimeter, not the slope, then what should you do? You remember, ya shabab, the moment, the strain energy density for moment is m square L divided by 2EI. Am I right? Oh, were there 2, ya shabab? Let me go check it quickly. Yeah, 2EI. That's it. This is the strain energy density. So basically, what the Castigliano theory says is that if you assume that EI are constant, both of them, then the derivative is going to be like this. So you will end up having the integral of 1 over EI. M is the moment equation multiplied by the partial derivative of the moment equation by the force. Why? This is the direction of this is the force which we are trying to find the displacement in the direction of. Do you understand? I think nothing will clarify this more than an example. So let me quickly show you this example, and then we will have a very nice example, exam material example, which we are going to solve together. Now, what you see over here is a beam. This beam, if I want to draw it, has 2 cross sections. This one has a moment of inertia of 2I1, which is double the moment of inertia for this. That's a very nice problem. And the lengths are 2L, L over 2, L over 2, and we have a force F which is applied on the end. Now, what the question is asking us to do is to find the deflection at points A and B. Do you see that? The deflections at point A and B. Now, at point A, we have a force, so we are covered. We don't have a problem. But at point B, we don't have a force. So with what should we take the partial derivative? We don't know. So what should we do? We put a fictitious force. That fictitious force is called QI. Okay. Now, let's talk about the first one, which is the easy one. The derivative will be taken with respect to F, and there is a force there. So the deflection at A will be equal to the partial derivative of the strain energy with respect to F. That's it. So before we do that, we know that we are dealing with bending, so we need to find the bending equation. And this is probably gonna solve this mysterious question in your mind, which is, we'll take the derivative with respect to what? Well, with respect to an equation. So let's see. Now, if you have a beam like this, which has been subjected to a force F, then the moment equation M is going to be equal to what? Minus Fx. Very simple. Why? Because this is Y and this is X. Now, if you cut the beam at any point, regardless of the fact that the diameter here are different, we're just finding the forces, the moment, then you will end up anywhere with how much is the force F multiplied by X. That's it. X is the distance. The distance goes from here all the way to the end. Do you see that? So what happened over here? If you see, the delta A is equal to the partial derivative of U with respect to F. Now, if we use the equation that I showed you earlier, we will integrate from 0 to L for 1 over EI, and then we multiply M by the partial derivative dm over df with respect to x. Now, there is one little problem over here. This is the general equation, but we know that I is not the same for the length from 0 to L. So what do we need to do? We need to split the equation, okay? We need to split the equation. So how do we split it? We say that this is 1 over E, then we integrate from 0 to L over 2, and then 1 over I1. From 0 to L over 2, the moment of inertia is I1. Then what is the moment equation? I don't want to confuse you over here, but look, we need to put the moment equation, which is what? Minus fx. And then what is the derivative of the moment equation with respect to f? You see that? So if the moment equation is minus fx, then the derivative of the moment with respect to f is going to be minus x. Very simple. That's why you have minus x. And then dx. Then we integrate from L over 2 to L. Now I is 2I1. The equation is the same. This is minus f over minus fx, and this is minus x. When you integrate, substitute, what do you get? You get the equation. Look at it. This is similar to the equation in the superposition. It's giving you the delta. Now, can you imagine this is the delta for that beam due to the application of a force F. And look how nice it is. If you have any beam made up of a moment of inertia I1 and I2, which is equal to 2I1, and the length here is L over 2, and the length here is L over 2, all what you need to do is to give me the force over here. Tell me what is the total length, what is E, what is I, and then I can find you the displacement. How much down this would go. Now the question is, how can I deal with the fictitious force? I am pretty sure you have 10 million questions about that. Now, let's see how do we deal with the fictitious force. And you will see why you need to have an equation, you need to have a force, because if you take the derivative with the fictitious force and you don't have an equation as a function of that fictitious force, the whole derivative will go to zero. You will have everything going to zero. So what is the deflection? Now, we know that the beam, ya akhwan, is going to deflect like this. Am I right? Let me make it clear. It's going to deflect like this. So the deflection at this end A is bigger than the deflection in here, right? But still there is deflection. So that's what we want to know. Now look, the first thing that we need to do is this, is to put the fictitious force. And when we put the fictitious force, what are the consequences? Now, here we have the beam like this. We have F over here, and we have a Q over here. Just imagine that Q is a force. And then we have X going this way, and this is Y. So if somebody asked you, what is the moment equation for any part of the beam over here? When you cut the beam anywhere, you make a cut, you get a reaction like this, and you get a moment reaction like this, and then a force like that. So anywhere here, from 0 to L over 2, the moment equation is minus Fx. Nothing changed, but the length is from 0 to L over 2. Now, what is the moment equation from L over 2 to L? Now look what happened over here. The moment, ya akhwan, okay, is going to go from 0 all the way to the maximum and the end. Now, putting a Q to it means that the part of Fx is going to be there, and then you will end up adding to it the part for Q. So the moment equation, if you make a cut over here, you will end up with the following. You will end up with the cut, a reaction moment, and a reaction shear. And then you will end up with a force F and a Q. So the equation will become minus Fx minus Qi, which is the fictitious force, but the location was not from X, because X start from here. We will start from X, but we need to take this part out. This part is what? Is L over 2. So we will start from X, but we will always eliminate the green part, because Q is applied after the green part, after this. So we don't consider this. That's why we put X and we subtract from it L over 2. Now look what happened. If I take the derivative of this equation with respect to Qi, I will get 0. Why? It's not a function of Qi, right? But if I take the derivative of this with respect to Qi, what would I get? I will get minus X, because This is the part of Q. So I will get X minus L over 2. Now, how is this going to end up being substituted? Look, the deflection at point B is equal to 1 over EI1 from 0 to L over 2. We're talking about Q, huh? And the moment equation is minus F over minus Fx. But what is its derivative? dm over dq is 0. It's gone. Plus 1 over EI. I here is 2I1. And then from L over 2 to L, which is minus Fx, multiplied by what? The derivative. The derivative was minus X minus L over 2. So this one is integratable. This is all 0. I don't need to do anything about it. So I go and do a multiplication, then integrate with respect to X, and then substitute from L over 2 to L, and you will get another equation. Now, beautiful. Look at this. This equation is telling you there is, by the way, let me ask you a question. Where is Q? It's gone. It's gone. Do you know why? Because before you integrate, if there is a Q, you should make it 0. Look. This integration is done. So you don't integrate. You first substitute Q equals to 0, and then you integrate. And here, we didn't have a Q, right? Or we did? We did. Do you know? Did you forget? Let me show you. I know I talk almost an hour, but I want you to, I promise I will end this soon. This part is what? This is the moment for L over 2 to L. If you go here, what is the moment equation for L over 2 to L? It is this. You see? So it is minus Fx minus Q multiplied by X minus L over 2. So why I only have this? Because the moment at Q equals to 0 is equal to minus Fx minus Q, which I am going to make it 0, multiplied by X minus L over 2. So what did I do? When I substitute Q equals to 0, all of this is gone. That's why I have only this one. Because the Q is 0. And the interesting thing is this. You substitute Q equals to 0, and then you integrate. And what do you get? You get everything as you expect. Give me the force that you will apply in the end. I know the beam is going to curve like this, and I am going to tell you, sorry, I didn't do it in a nice way. Let me clean it up. So if the beam is like this, and then you applied a force like this, we know that this is going to deflect like this. So this is deflection at A, this is the deflection at B. The deflection is supposed to be related to F, which is true. Look at this equation. It is related to F, L, E, and I1. I1 is the same, except that here, this is 2I1, and this is only 1I1. You understand? In the next, inshallah, class, we will talk about this example. This example, quickly, what do we have? We have a simply supported beam with a length L and two forces, P and P, located at A and A from the ends. And what do we want? We want to find the maximum deflection, where the maximum deflection is going to be in the middle. So what are we going to do? We are going to put a fictitious force Q in the middle, and we will solve this problem. Okay, thank you so much.